Okay, so we're here to do a divergence theorem example. So here I have a problem and some instructions. I'm supposed to calculate a flux of a vector field through a surface S using the divergence theorem. And they give me a vector field F, which looks like it sucks. And S is a surface of a solid bounded by a paraboloid z equals x squared plus y squared, and the plane z equals 4. So first things first, I'm hoping we remember that a paraboloid is one of these guys, and that if we cut it through with a plane, we'll get some kind of a satellite dish looking shape. And actually I can see that edge, so I'm going to put a boundary on there, and then we might put another kind of like that, right? So we've got circular paraboloid. You guys may be familiar with one of these. Ought to be, I hope. This one is pointed directly up, so the z-axis kind of comes up out of this thing. That is our z-axis there. The x and y axes are maybe over this way and back that away or something. Cool. Hoping that's a start. Should be noted at the top there, that is the plane z equals 4 intersecting the surface z equals x squared plus y squared. So that's given by z as 4 and also x squared plus y squared is 4. I'm going to write that as 2 squared for no reason in particular. Sure, you guys, no clue why I would do that, right? Like, okay. So we did that to figure out what the radius of this circle is. Okay, so first things first, I need to set up my problem. So the thing they asked me to compute is the double integral over my surface, right? That's just the skin of this thing of my vector field. So my vector field is cosine z plus xy squared, comma, x e to the minus z, comma, sine y plus x squared z. Okay. ds. And I would have a rough time doing this. It's not like it's impossible. It's just kind of annoying. So I've got two separate surfaces that I'm going to have to parameterize. Need to calculate some cross products. It's not so bad, but like we can do better. So the divergence theorem tells me that instead of calculating the flux through the skin of the thing, I can calculate the total of the divergence inside of it, assuming a little bit that it's oriented outward. They didn't explicitly tell me this is oriented outward. I'm just going to kind of have to assume that it is. Okay, whatever. So we're going to triple integrate over our little parabola bowl guy. That's my drawing of a little parabola bowl guy. That looks like trash. I'm going to call it E for inside. And then we're going to triple integrate. And the thing we're going to triple integrate is going to be the divergence of the vector field that they asked me about. So that's a, let's see, x partial of that stuff is a y squared. The y partial of the middle stuff is 0. And the z partial of the last stuff is an x squared. And then I need to be integrating d volume. Okay, now I need to pick a coordinate system. That thing there probably lends itself to cylindrical, because if I had to think up, I'd look at this bottom thing and be like, well, that shape is z is x squared plus y squared, and x squared plus y squared is actually just r squared. Okay, that feels way too easy. Oh, and x squared plus y squared is also over here as r squared. Oh yeah, this is meant to be. Okay, so we're going to need bounds for our triple integral. We're going to be integrating r squared. Then we need a times the dv for cylindrical is an r dr d theta dz. Okay, so that's this guy here was my, so r squared came from x squared plus y squared, and the r dr d theta dz came from the dv above it. Okay, now I need bounds. So Let's see. Bounds are going to be a function of my shape. Oh, okay. So the z's go from zero. No, this is maybe the tough part. The z's don't go from 0 to 4. They actually go from r squared to 4. So there's two places where r squared had to come in. One was because of the divergence thing, and the other one is because of the z equals x squared plus y squared part. So that the dz can't go out there at the end. I need to put it in an earlier position. So I'm going to swap the dz to the front. And the z's are going to go from r squared to 4. And then once I flatten that, so if I take this thing and mush, in the xy plane, right? So after I integrate these e's out, I'm going to get just that circle. That's going to be a radius 2 circle because that's how big it is when it hits the top, right? So that's the biggest we get when we smash. So my thetas go from 0 to 2 pi because we have the whole circle, and my r's go from 0 to 2 because that circles of radius 2 up at the top. Okay, now I actually have some work to do. So let's see. I'm gonna get a 2 pi out anyways. So that guy's gonna kick a 2 pi. And then the rest of this I'm gonna have to work for. So I've got an integral from 0 to 2. And then I'm when I integrate r cubed dz, I get r cubed z. That's going to be evaluated from r squared to 4. And then I've got a dr still to sort. Notice that was a dz integral, so I didn't get a constant or anything. Really, I got a constant, but it was 1. And then I'm going to get a 2 pi. Then I've got integral. Oh, no, I should just evaluate. So I've got an integral from 0 to 2 of 4r cubed minus r to the 5th, I guess, dr. That got a little ugly on me. Let's see. Did I do that right? Yeah, I think I did that right. Okay, cool. When things get ugly, you might want to like think about whether you screwed it up. Just saying. Okay, so I got a 2 pi, and then I need to integrate both of those. So that's going to be a let's see, r to the 4th over 4 times a 4. So we're going to cancel a 4. We're going to get an r to the 4th. Okay, that makes me feel better about my life. Minus an r to the 6th over 6. That makes me feel worse about my life. Then we're evaluating from 0 to 2. Okay. Well, so I guess I get 2 pi times r to the 4th is like 16 minus let's see, that's actually going to be 2 to the 5th over 3, so that's going to be a 32 thirds. And let's see, 16 is 48 thirds. So all told out of this, looks like I get 2 pi times 16 thirds. That feels weird. Is 32 pi over 3. Okay, cool. Check done, probably. I feel pretty good about that.